Morning, everybody. Today we are going to continue to look at our similar triangles. But instead of looking at the ratios of the sides from one triangle to the other, instead today we're going to be looking at the ratios of the sides within the triangles, which you can obviously see this is a triangle despite all of the curves and the hypotenuse. Man, did that turn out to be an ugly triangle. Anyway, we've got these two triangles, and we do not know if they're similar yet. But this is going to be our 3, 4, 5. Don't know, I'm a big fan of 3, 4, 5s. 3, 4, 5. And this looks to be about, twice as big. So I'm going to call this my 6, 8, 10. Just so it looks like I'm working with everything to scale here, which is something I don't normally do. You're welcome. So, looking at these two triangles, we can determine if these are similar by looking at the ratios of everything. We built some of these last week. Okay? Let's put our larger triangle on top because that's what we had been doing, starting with the smallest side to the largest side. So 6, 8, and 10. If you're at this point, you should have already been done with the corresponding sides assessment. So you should know that the shortest side will correspond to the shortest side, so 6 to 3. The longest side, 10, will correspond to the longest side, which is 5. And then the middle sides will correspond to each other. Now, if when I do this division, I get the same numbers, we know that we have similar triangles. 6 divided by 3 is 2, 8 divided by 4 is 2, and 10 divided by 5 is 2. So we had the same ratio. We doubled the length of all of the sides. So we know these two triangles are similar. And I constructed them that way. So when we have two similar triangles, what I want to show you today is that the pieces are always going to be in ratio with themselves. And what I mean by that is if I look at, say, the shortest side to the longest side, and I write that as a ratio, so 3 to 5 equals the shortest side to the longest side, 6 over 10. 3/5, if I reduce 6/10, that will also be 3/5. So the relationship between this side to this side will be the same as the relationship between this side and this side. Let me show you another side. Let's say our shortest side to our middle side, so 3/4 equals short to middle will be 6/8. Again, we'll simplify 6/8 down, and 6/8 when it reduces will be 3/4. So the ratio there is the same. So not only can I double everything here to get over here, I know that my ratio of 3 to 4 is true over here as well. So what I did to go from 3 to 4 is multiply by 1 1/3. Over here, to go from 6 to 8, I multiplied by 1 1/3, which I think you'll see if I make up some different numbers. So that's what we're looking at today, is comparing the sides of the triangle inside of itself, which will be especially useful when we get to some trig stuff. So none of this is going to be to scale, and I'm sorry, I wish that it was, but it's just not going to be, because that's the life that we're living. And you know what? We're going to get through it. All right. So let's say that I've got like a 6 here and a 12 here, and I don't know, let's call this 8. Okay, so I've got a 6, 8, 12. If this is going to be similar, let's say it's half as big. For it to be similar, that means that all of these will need to be cut in half because they need to maintain that ratio. So 6 will become 3, 12 will become 6, and 8 will become 4. Because now they're in ratio. All of these sides are twice as big as all of these sides. So I've got side, side, side. I know we're similar. Okay? So looking at this, I notice that to go from this side to this side, well, this is just twice as long. So 6 to 12, I multiplied by 2. And the same thing happens over here. This side is twice as long as this side. So those ratios get maintained. Over here, to go from 4 to 6, I multiply by 1 1/2. Half of 4 is 2. 1 1/2 of 4 is 1 of 4 and half of it. So 6. So 1 1/2 of 4 is 6. 1 1/2 of 8 is 12. So the ratios inside of the triangles are the same. And another reminder, because this will also help when we get to trig, is that these angles, because the triangles are similar, are going to be congruent as well. And that's going to be a big deal when we get to trig, okay? Which is maybe what we hit next, okay? So that's what we're looking at right now. Let me give you an actual problem. And I'm going to actually pause it while I write. All right, so I've come up with a problem. Now, do you need the new stuff that we talked about today to understand and be able to solve this problem? No. You can use the ratios from last week and you'll be fine. You can still do 5 over 8. 5 over 8 equals x over 24, because 5 over 8, those are my corresponding sides. X over 24, I put the smaller triangle on top in both spaces. 5 and 8 are corresponding. X and 24 are corresponding. Cross multiply and you'll be able to solve. Okay, that'll work out. You can still do that method. But what I'm looking at right now is seeing that 5 to 8 is kind of ugly. That's going to give me a fraction. That's going to be 1 3/5, 1.6. I don't want to deal with that, okay? But I also notice that these sides work really, really well together. 8 to 16 means that I just double to go from my shorter side to my middle side. And my shortest side to my longest side, I just multiply by 3 to go from 8 to 24. So I can do that really, really quickly. That's much easier math for me. So to get my longest side, I take my shortest side and multiply by 3. 5 times 3 is 15. To get to my middle side is my shortest side multiplied by 2. So y will equal 10. Okay? So it's much easier to see that. So maintaining these ratios is also something that similar triangles do. And again, when we get to trig, it'll be a big deal, because we're going to start asking ourselves, what is this angle measurement? And we don't know, but we know that because this angle measurement is the same as this angle measurement, the 8, the 24, and the 16 will all maintain the same ratio as a 5, a 15, and a 10. So no matter what the triangle looks like, how big it is, the angle measurements are going to stay the same as long as we can figure out what the ratio is between the sides. So that's why we're looking at side ratios today. Let me give you a problem to try on your own. And then what we're probably going to be looking for after today is probably a big ratios and similar triangles assessment interview, and then jump into some trig stuff straight from here. Yeah, trig stuff would make the most sense. All right. If I have a triangle, there are sound effects to drawing because I've been quarantined for 4 weeks. Let's take a look. I'm going to call this 4. I'm going to call this 8. I'm going to call this 7. And I'm going to call this 14. X, Y, we're going to make these. All right. We know these are similar triangles because we've got congruent angle pairs all over the place. Take a moment and you can build the ratios if you want to build the ratios, but I think that if you look at this, hopefully you'll notice that there are some pretty simple ways to look at the relationship between sides in triangles and solve for x and y pretty quickly. Go ahead and take a second to work on that. All right, so talking about some of these ratios inside triangles, you can write this as 4 to 7 equals x to 14, and you can solve that way. And it'll work out. That's the stuff we were doing last week, and it'll be totally fine. No worries, no problems. But looking at what, excuse me, what we've been talking about today, I see that this side, which corresponds to this side, and this side, which corresponds to this side, in order to go from here to here, I just double. 4 to 8 is just multiplying by 2. So to go from this side to this side, I just have to multiply by 2. 7 times 2 is 14. Now, I don't know on this side what I need to do from 4 to x. But I know over here to go from 7 to this 14, I just doubled. And all of the sides work out this way. So this corresponding side to this corresponding side, I just doubled again. So x will also equal 14. So we have an isosceles triangle here. Okay, so that's the kind of stuff we're looking at today, looking at the ratios within the sides. Let me give you something that's going to end up with some fractions, because that's also a good thing for you to see, and then we'll jump into the homework. And I'm just going to have you try this problem. Give me a second. I'm going to write it, and then you'll be good to go. All right, I've got a problem here for you. Go ahead and take a second and find x for me. Go. All right, looking at this problem. We can do, as we've been doing, 4 to 6, which are my corresponding sides. I put my smaller triangle on top. So for 6 to x, and we can cross multiply, and we'll get 36 equals 4x, divide by 4, and x will equal 9. Okay? The other way that we can do this is seeing the ratios of within the triangle to within the triangle, which is 4 to 6 equals 6 to x, which actually ends up being the same problem because I used too many 6's. But again, cross multiply, and 4x equals 36, which will give us x equals 9. The last way to think about this is what times 4 gave me 6? 1.5. 1.5 times 6 will give me this x, or 9. Okay, so very similar to what we were looking at last week. The last thing that I want to talk about just a little bit here is, because this is a 9, and these are right triangles, okay, so I know that these are both 90. This 4 and this 6 have the same ratio to each other as this 6 and this 9, which means that these angles are going to be congruent. And as long as this is the angle measurement, the ratio of these two sides will stay the same no matter how big or small the triangle gets. The ratio from side to side inside the triangle stays the same. So we'll talk about that when we get to trig. So keep that rattling around in the back of your brain, because that's how we're bridging the gap between what we're working on now and what we'll be working on later. Okay, there's homework inside Schoology. Go ahead and get.